Hello everyone, I'm Saher and the topic for my literature review and presentation is the Swin transformer. The evolution of network architectures in natural language processing has taken a different path. And today, the prevalent architecture is the transformer. A transformer is a transformer based deep learning model with state of art performance in vision tasks. And because of this, it really has very high efficiency and greater accuracy. These are some of the desirable properties due to which Swin transformers today are used as the backbone in many vision tasks. But to proceed forward, we would need a bit of the background of vision transformers in order to better understand Swin transformer. Vision transformer, or even famously known as VIT, is a model for image classification that has a transformer like architecture, and it even acts like a transformer type architecture over patches, or I would like to say tokens of the image. So basically here the image is split into fixed size tokens. As you can see over here, it's split into fixed size tokens. Then there is patch and positional embeddings that are added upon these tokens, and the resulting sequence of vectors is then fed into a standard transformer encoder. It is just exactly what a normal transformer encoder would do. Now, in order to perform classification, the standard approach of adding an extra learnable parameter, also widely known as classification token, is used. The work of a VIT or vision transformer is very much similar to that, or I could say directly applies a transformer architecture on non-overlapping medium-sized image for image classification. It achieves and quite impressive speed accuracy on image classification when you compare it with different convolution networks, but yet VIT requires large scaling training data sets to perform. So that really serves as a very big disadvantage. The results of VIT on image classifications are encouraging, but still the architecture is quite unsuitable for use, and especially for the use as a general purpose backbone network because of its low resolution feature maps and the quadratic increase in complexity with image size. In order to address these issues, the Swin transformer comes into play. The Swin transformer is a general purpose backbone for computer vision, and it was introduced with the representation of computation with shifted windows. The shifted window scheme brings greater efficiency by limiting self-attention computation to non-overlapping local windows while also allowing for cross-window connection. I get it. There are words that have been used which are quite impossible to understand now, but it gets better as we proceed. The hierarchical architecture has the flexibility to model at various scales, as well as it has a linear computational complexity with respect to image size. In short, by the word feature maps, I mean that they are basically intermediate tokens that are generated from each successive layers. As you keep forward, there are certain tokens that are generated which keep the features of the map safe. And for hierarchical, I refer that the feature maps are later on, as we proceed deeper in the network, they kept merged to each other by reducing the dimension. These qualities of Swin transformer make it compatible with a broad range of vision tasks. Some of that could be for image classification, for object detection, and semantic segmentation. Well, first thing that we need to do over here is to understand the structure of the Swin transformer. Now, this is the structure of the Swin transformer. And as you can see, it is mainly divided into four main components. The first would be path partitioning, linear embedding, Swin transformer block, and patch merging. Several transformer blocks with modified Swin transformer blocks are applied to these tokens. The transformer block maintains the number of tokens H by 4 and W by 4, and together with linear embedding is referred to as stage 1. To produce a hierarchical representation, the number of tokens are reduced by patch merging. So patch merging is the one that is responsible for the hierarchical representation, and also it reduces the tokens as we keep going deeper down the network. And the first block of patch merging and feature dimension is donated at stage 2. As we can see, stage 3 and stage 4 are nothing but the repetition of stage 2. Now, let's better understand each block, what each of the blocks are doing. So, the first that we have is patch partitioning. The first step consists of splitting an input RGB image into non-overlapping smaller patches. By patch, I mean token. So moving forward, I would use the word token in order to avoid any confusion. So now each token is basically a concatenation of raw RGB values. So in the paper here, they have used 4 cross 4 tokens. And so the feature dimension would be 4 cross 4 cross 3, which is equals to 48 vectors, where obviously 3 is the RGB channels. Moving forward, we have the linear embedding layer. There's not much that's going on in the linear embedding layer. To be putting it directly into one word, a linear embedding layer is applied to project it an arbitrary dimension C. So this 48 dimensional feature vector is getting converted into an arbitrary dimension C, where C basically determines the capacity, or maybe more ease, the size of a transformer model. And it also somewhat determines the number of hidden units that are present. Now, as we know that several Swin transformer blocks are applied on these tokens moving forward. But before understanding what a Swin transformer does, it is better to understand what basically happens in patch merging, and then we can move forward with Swin transformer. So now we have the patch merging. The convolution-free downsampling technique that is used in Swin transformer is known as patch merging. So basically, in this context, token obviously refers to the smallest unit in a feature map. To downsample features by a factor of, let's say, n, patch merging concatenates the features of each group of n cross n neighboring patches. I know it can be a little difficult to understand, so for this reason, I've added an illustration. Let's just have a look at it. Yeah. So as we can see from this animation, patch merging groups each n cross n neighboring patches and concatenates them depth-wise. As you can see over here, these are getting concatenated depth-wise. The effectively downsamples the input by a factor of n. As you can see, the input is getting down factored by a factor of n. So basically, h is becoming h by n, w is becoming w by n, but if you notice over here, n is getting increased by twice. So it becomes n squared c. Now let's go back to this slide. Okay, so we're basically reached this place where our h is converted to h by 2, w is become w by 2, and c has become 4c because this is n squared c. The purpose to fuse patches is to introduce a hierarchical feature representation. The feature dimension of each new patch is now changed to 4c. I think that's clear. The dimension is then reduced to 2c by applying a layer norm to reduce the subsequent computation. In order to reduce the computation, we apply a layer norm and convert this 4c to 2c. The dimensionality is then kept constant after the Swin transformer passes through the Swin transformer block. Well, in fact, if I were to say, the dimension of the input doesn't changes as it passes through any stage in patch merging. It is in fact in between the stages that a patch merging layer is applied to reduce the number of tokens as the network gets deeper. So now we have the Swin transformer block, which is the main aim of the paper. The traditional transformers, they compute attention based on global picture. So the computational complexity is really high. As we see, the Swin transformer block, it consists of MSA, which is multi-head self-attention, and you can see there are two. W stands for window-based and SW stands for shifted window-based. Then there is layer normalization and two MLP. A layer norm is applied before each MSA module and each MLP, and a residual computation is applied after each module. Now this MSA, as I have mentioned, is classified into window-based MSA and shifted window-based MSA. So let's move forward and understand what is basically happening in window-based MSA. Here, Every token in a local window is attended to every other token in that window. Okay, let's make it simple. So, what is basically a window? A window is nothing but simply a collection of tokens, and computation is happening only within each window. Now, this is a token. This is a window. This is a window. So this patch was divided into four windows. Okay. For example, and this illustration below uses a window of size 2 cross 2 patches, and window based MSA computes attention only within each window. Now this window is having computation with respect to just these patches. This is having with this, and this is what happens. But if you notice over here, the very obvious thing that is happening is that MSA is restricting self attention to each window. And this, in fact, leads to limits on the modeling power of the network. And in order to address this issue, Swin transformer uses shifted window based MSA module after window based MSA module. So first you have the window, and then you have the shifted window, because the window based MSA module has a limiting self attention, and that is the reason to overcome this we use shifted window based MSA. Here there is a concept of cross window connections. Shifted window MSA shifts the windows towards the bottom right by a factor of m by 2. So if you notice over here, the window is shifted by m by 2, where m is nothing but the window size. However, if you notice that when this shift is performed, there are many tokens that can now be referred as orphan tokens, and they do not belong to any window. In order to not make them inorphaned, we perform the cyclic shift, in which certain orphan tokens are replaced in order to fit in a window. For example, when this is shifted by a factor of m by 2, these tokens are shifted down, these are shifted towards the right, and these are shifted diagonally. The key design element of Swin transformer is its shift of window partitioning between consecutive self-attention layers. The shifted windows bridge the windows of the preceding layer, providing connections among them that significantly enhance modeling power, and it also introduces the important cross connection between the windows. And this is found to improve the performance of the network. But if you notice, after the shift, a batched window may consist of several sub-windows that are not adjacent to each other in the feature map. And to resolve this problem, a masking mechanism is employed to limit self-attention computation to within each sub-window. With this cyclic shift, the number of batched windows remain the same as that of the window partitioning. This is somewhat a basic idea of what a Swin transformer architecture looks like, but it would be great to see what are the results of the Swin transformer in today's world. Talking about results, these are few of the results of Swin transformer. As you can see, image classification is being done on ImageNet, and it is being compared with state-of-art convolution nets. And we can see that the Swin transformer achieves a slightly better speed accuracy trade off. But this slightly is top one accuracy, so we know that it really matters. The Swin transformer is probably the most exciting piece of research, obviously followed by the vision transformer. And as far as for me, it is really an exciting piece of research because it uses the concept of hierarchical feature maps and shifted window MSA. And obviously, it resolves all the issues that were present in the original vision transformer. Today, the Swin transformer is commonly used as a backbone architecture in a broad range of vision tasks, such as image classification and object detection. For references, I've attached the reference of the original paper of the Swin transformer, and in case if anyone wants to read more about either of them, you can read. And if someone has grabbed attention on Vision Transformer, this is the original paper and it's worth a read. Thank you so much.